Welcome to another CO2 Monday in the Refrigeration Mentor Podcast. I'm your host, Trevor Matthews. And today, once again, I have a special guest, Parham. Parham's been on the podcast a few times before. We were talking about CO2 pressure enthalpy versus temperature. We talked about purity of CO2, but we're going to get into a great conversation today because it's something that I'm learning more about: ground source heat pumps, but not only ground source heat pumps, CO2 ground source heat pumps. I'm super excited. I have lots of questions. If you have any questions, please shoot them in the chat on this live video. If you're listening to the podcast, always share. Please leave a comment. Please give it a review. This is how more people find out about the Refrigeration Mentor podcast. Parham, welcome. How you doing, brother?
Hi, Trevor. Hi, everyone. Thank you so much, Trevor, for the invitation. It's always a pleasure talking to you and discussing these in very interesting CO2 projects. Excited to be here and talk
Well, I
about
love
that.
talking to you because I learned so much. You spend so many years in CO2 and learning about it and research on it, like diving in deep into from different studies, writing your own studies, training it, teaching others. And this is how I learn, right? Is asking the experts like yourself. Param, why don't you give a little brief background on your CO2 experience as well, especially for the ground source heat pump side?
Yeah. Actually, after my PhD project, which was on ground source heat pump specifically, but not on CO2 ground source heat pump, it was more secondary loop ground source heat pump that I'll talk about it during the presentation, just give you some information about different types. Then after my PhD, I decided to continue on the field of ground source heat pump. But since I know that the problem of ground source heat pump is the cost, the high initial cost of that, especially for residential application. So we decided to do research on trying to reduce size of the ground heat exchanger and therefore the cost of the system. And just one option was working and finding different working fluid for ground heat exchanger part, and actually doing a research on different type of refrigerants. We found that CO2 had some great potential for this technology to be able to reduce cost and therefore to make it more affordable for people to have to install ground source heat pump. So I'm going to talk about a little bit about this and the comparison between refrigerant and why we're saying that CO2 has a great potential. But that was the kind of the history behind that. So after my PhD, I started doing research on different refrigerants in ground source heat pump, and then we found that CO2 is a good option to be used for ground source heat pump, and it's been almost 10, 12 years working on that, and we published many articles on that subject. Most probably I try to summarize that in few slides for you today. And of course, they are all available. People who are interested, I can even send them a copy of those to get more information about the project.
Yeah, if you have research documents that are online that I can put in the show notes or in the comments where people can go and read them, because I know there are some people that are interested in learning the in-depth stuff. Some other people just wants the quick down and dirty, like we're going to talk about today, because we only got an hour here and we're going to talk about ground source heat pump as much as possible. Let's start off and talk about what actually a ground source heat pump is, because I kind of have an idea, because we're trying to use the ground to exchange heat. But what is a ground source heat pump?
Yeah, that's an excellent question. I prepared a couple of introductory slides for everyone, just to be able to know a bit more about ground source heat pump and different types, and then we go into more details using CO2 for ground source heat pump. Ground source heat pump basically is a heat pump that is linked to ground. It takes heat, like imagine if we consider that for heating application, ground source heat pump takes heat from the ground and boosts that heat using the compressor and deliver that heat at higher temperature to heat the space inside the building. So basically, we use the ground as the heat source, low temperature heat source, to be able to run our heat pump and generate some like heat for high temperature heat for our building. Or in cooling mode, it can be also reversed and use this system for cooling. And in this case, we reject heat to the ground instead of extracting compared to heating mode. So basically, always I say that ground source heat pump is the most efficient technology to heat and cool buildings, and even for water heating. It's the most efficient technology. But there are always some barriers for adoption. So the main barriers are high initial cost, of course, and for heat pumps, basically is today we are talking about is use of synthetic refrigerants, which could be not good for our environment. And also the other barrier that we see these days is lack of knowledge and good tools to design, because we tend to either oversize the system, and this create even more initial cost for the project, or in order to make it more affordable, we tend to undersize the ground heat exchanger, which is not good either, because the operational cost would be significant, and sometimes even the system doesn't work in the peak condition. So that's why some people say, okay, ground source heat pump is not good because we pay a lot of money and then it's not working properly. So this is all about sizing it right to be more efficient or get the efficiency that we expect, and also to be affordable, or at least close to other systems that we can install in terms of payback period.
Okay. So my understanding is that, like you said, you're taking heat from the ground or using the ground as the option. From my understanding, and you might get into this, there's a couple of different ways to do it. Like I know some friends who do ground source heat pump, and they have to drill holes into the ground like 300 feet or 100 meters into the ground, real deep. So that equipment to do that costs a lot of money. And other people I've talked to, you need to just get like really below the frost line, 4 feet or 6 feet down below, wherever you're at. I think it's 4 feet, 1 or 2 meters down below. And then you can do like a long horizontal one. Is that the two options, or is there other options as well?
Exactly. There are many options in doing that, but there are different classification or categories. Like as you mentioned, we have vertical ground heat exchangers and horizontal ground heat exchanger in one classification, for example. And you said that it's deep. We drill deep. This is considered, when we couple that with heat pump, it is considered shallow ground source heat pump or shallow geothermal system, because when sometimes we talk about geothermal and the people think about very deep, like 1 kilometer or 2 kilometers to generate steam for electricity generation. So this is what we're talking about today is shallow geothermal, which is around what you mentioned, like 300 feet or 100 meters, or sometimes it goes as deep as 200, probably 250 meters. But of course, there are different types. Vertical one is you drill vertically into the ground, like 6 to 10 inches of the diameter of the hole, and then you run U pipe inside to be able to circulate the fluid inside and extract the heat from the ground, and also horizontal ones. But the most efficient system is vertical, of course, because in horizontal system, you have the top 6 or 7 feet from the surface, is you get some influence from also the ambient temperature. But when you go below that, the temperature of the ground is almost constant over the entire year, so it doesn't change much. That's why this vertical system is more efficient than horizontal system. But of course, horizontal system is less costly compared to vertical system. So there are different options, and each gives you different performance. So depending on the project, the electricity cost, we have to find the best that in terms of also like dollar saving makes sense to for the project. Basically, these are the types that you can, some of them, not even all. So as I mentioned, the closed loop, we have the vertical ones or the horizontal ones. And we have also the open loop system that we take the groundwater directly in, we pump it from the bottom of the well into the system, the heat pump, and circulate the groundwater into the heat exchanger to extract the heat from the groundwater. So in this case, we have to run the system above 0 temperature so that we don't freeze anything. But they are very efficient system, the open loop system. So probably if you don't have enough space to drill many boreholes, probably one option that you can consider is those open loop systems.
So for an open loop system, I don't really know anything about those. So you'd go down, you'd hit the water, there'd be your water zone, wherever that is, however deep it is, and you'll be actually just sucking up the water from the ground. You must have to have some sort of filtration system going through there? How does that not plug up the pump and all that stuff, like dirt and stuff like that? Would you know?
Yeah, of course, there are some filtration system, and also when you take it from one well, you have to reject it back to another to make that circulation inside the ground also for heat transfer. But you always have a filtration system, and it really depends on the water that you're taking from the ground. The filtration could be different, and this also could be a costly part of the operation of the system. They are pretty efficient. Those open loop systems are pretty efficient. But today, what we're going to talk about more closed loop and using CO2 as heat carrier fluid, or maybe the refrigerant inside even the ground loop. So that's why we call that. This is today we're talking about another classification, which is two different systems. One is a direct expansion ground source heat pump, or secondary loop ground source heat pump on the right. Let's first talk about secondary loop ground source heat pump. This is the conventional type of ground source heat pump, where you have your heat pump and there is a separate loop for the ground loop. In the ground loop, you have a pump, a dedicated pump to circulate the fluid, which is most of the time is mix of antifreeze and water. And there is a above ground heat exchanger to be able to exchange heat with the refrigerant, like that fluid, that secondary fluid with the refrigerant in another heat exchanger.
Yeah, I've seen those ones before, like the secondary loop ones before.
Yeah, as you can see, this is the heat exchanger. That one side of the heat exchanger is the secondary fluid, and the other side is the refrigerant. So what happens, imagine you run this system for heating mode. This is going to be your evaporator, this heat exchanger basically. And on one side, you evaporate the refrigerant, and on the other side, you have your single phase fluid, which goes through temperature change, not phase change. This is this secondary loop. And the pump is to circulate the fluid inside the heat exchanger and to overcome the pressure drop inside the ground heat exchanger. So that's the conventional system that we most of the time use for different projects, either big projects or small residential projects. But I have to say that residential project, at least in Canada, it doesn't, that like ground source heat pump is not really, like payback period is pretty long. So most of people, it doesn't make sense to install ground source heat pump for a small residential building because it costs a lot and they have to wait 15, 20 years to get back the investment in terms of energy saving. But the other system that today we are going to focus more on is the direct expansion ground source heat pump, this schematic over here. So as you can see, there is no pump, extra pump, and there is no heat exchanger. So basically, the ground heat exchanger is an integral part of the system. In this case, if in heating, for example, this is going to be the evaporator of our heat pump system. So basically, when the refrigerant is coming, liquid refrigerant is coming in, if we evaporate the refrigerant and then we send it to the compressor. But in the cooling cycle, it's going to be the condenser, and we condenses inside the ground heat exchanger. That's why in this type of ground source heat pump, direct expansion, we either evaporate or condenses, and we have two-phase fluid inside the ground heat exchanger. So it's like whatever happens in this small heat exchanger for secondary loop, it happens over here for direct expansion system. Because of that, there are some advantages and some disadvantages for direct expansion system. So one, the advantage is not using the pump anymore. So we don't need the pump in secondary loop system that we use. The compressor itself is able to compensate the pressure drop that we get in the ground heat exchanger during evaporation or condensation. And also, there is no need for this heat exchanger anymore. So when we add a heat exchanger, it means that we add thermal resistance to our system and makes the system a bit less efficient than it should be. By eliminating that heat exchanger and also the consumption, the energy consumption we put into the pump, we can make the system way more efficient. That's why, again, I said ground source heat pump is the most efficient, and among all those types, direct expansion ground source heat pump is the most efficient system that you can use to heat and cool buildings and even produce hot water for your domestic hot water application. And also the other thing that we say about direct expansion, especially in the ground heat exchanger, is we have, because of evaporation and condensation, imagine if there is no pressure drop or a small pressure drop, then the temperature, the fluid temperature or the refrigerant temperature remains constant from the beginning of, from the inlet of the ground heat exchanger to the end, because we evaporate, we change the vapor quality, not the temperature. So that's why we have the uniform heat transfer from the ground to the fluid or the refrigerant. But in secondary loop system, because the temperature increases, we get less over the borehole depth, we get less thermal extraction, heat extraction from the soil. So that's why one benefit or one advantage of direct expansion is to get like the uniform heat extraction along the borehole pipes. So the extraction amount doesn't change over the pipe length. Also, a smaller borehole is another advantage of direct expansion, because in direct expansion we use pretty small pipes, and therefore we don't need a big like 6-inch hole or 10-inch hole. Even by drilling 4-inch, we would be able to fit a U pipe inside, because the pipes are not as big as the secondary loop system.
So I have a question now. So you said with the direct expansion, you would have the same temperature leaving as the same temperature coming back. So there's no change in temperature as it goes out and then it comes back.
Exactly. So there is no temperature change because we go through evaporation or condensation. There is an exception, of course. For zeotropic refrigerant, of course, the temperature changes over evaporation or condensation. But for normal refrigerant, like a CO2 or not a mixture of refrigerant, you get constant evaporation and condensation over. For evaporation and condensation, you get always a constant temperature if there is no pressure drop. Of course, when there is a pressure drop, the temperature also changes. But if you assume that there is no pressure drop, the temperature doesn't change from inlet to the outlet. It's just the vapor quality changes. And therefore, we extract always over the pipe or the borehole depth, always the same amount. So the performance doesn't drop over the pipe length. Of course, there are some disadvantages for the system. When we have direct expansion system, we need to charge the system, even the ground loop, with refrigerant. So the charge of refrigerant is more compared to secondary loop system. And this could not be a big problem for CO2, because CO2 is not as expensive as some synthetic refrigerant, but still we need to consider charging the system more than secondary loop system. And also the oil circulation is another issue that people always talking about when we say about, like, we talk about direct expansion system, like oil circulation and oil return to compressor, it could be also problematic. But again, for CO2, because I'm going to talk about that later, that because we're not going to have that problem like other refrigerant.
Yeah. High pressure.
Yeah, high pressure, and also the pipe dimensions are pretty small. The velocity inside the pipe is pretty high, so we're not gonna accumulate oil at the bottom of the borehole. So again, for CO2, this cannot be considered
as long as it's designed properly, because if it's not designed properly, you got the pipe is too big and you slow it down there, you could run that in. But if it's designed properly, yeah, I think that's like a lot of systems, right? If they're designed properly, they're sloped right, you'll get the oil back.
Yeah, the other thing that there is a big difference for other refrigerant, there is a big difference between density of vapor and liquid, and that's why they need to size the pipe going down differently from the pipe going up in the ground heat exchanger in the direct expansion system. But for CO2, since the pipes can be sized pretty small, then even there is no need for having different pipe sizes.
Okay, so you're saying right now with, say, a synthetic refrigerant, the pipe going down is going to be a different size than coming up.
Yeah, the mostly for direct expansion, this is the normal practice that they use. They tend to size it different, like different sizes.
Okay. Would the one going down be smaller and the one coming
Yes,
up bigger?
in heating application, when we use the ground heat exchanger as evaporator, because we send liquid in the first pipe and we get vapor in the second one, yes. So in order to maintain the velocity,
Yeah. So now with CO2, potentially you'll have the exact same size going down and up.
yeah, because the pipes are pretty smaller, and especially with the configuration that I'm gonna talk about. This is the new concept that we try to introduce for this type of system. We don't need to size the pipes differently because the pipes are pretty small, but we have bunch of them in the ground heat exchanger. I'm gonna talk about
Yeah.
that.
Awesome. So is there a certain place where you can go and size this stuff? Like just say someone wants to size a ground source heat pump like that coil that goes into the ground or the pipe that goes in the ground. Is there specific softwares out there that you can do this?
Unfortunately, at the moment, there is no software to size. As far as I know, there is no software to size direct expansion ground source heat pump, especially for CO2, because the calculation, since we have two-phase flow, is more complex than when you have secondary loop single phase. And there are many assumptions you would take in order to do the calculation, and the validity of those assumptions for different refrigerant. Also, the correlation, the existing correlations for heat transfer, pressure drop is pretty limited for CO2 compared to other refrigerants. So as far as I know, there is no software that you can size the pipes. This is something that in close future, if we want really this system to be used more often for our projects, probably we need to develop.
So right now it's using off charts. Engineers are doing it off certain charts.
Yeah,
Yeah.
normally what the projects that I'm aware of, or the other researchers try to develop models, and based on that, I try to size the pipe sizes,
Perfect.
everything. And also the other problem could be in case of leakage, the ground contamination with refrigerant, which is not desired for this system, like to contaminate ground with the refrigerant and the oil. But CO2 again, probably less concern over.
Yeah. Like I tell everyone though, CO2 is natural, but you still don't want it to leak. Like this is a system. It's still bad for the environment. It's a 1 GWP. Yes, maybe if you leak 404, it's almost 4,000 GWP per pound, but it doesn't make a difference. It's still something you do not want to release because it's still, I know it's going to be regulated at some point. There's going to be, you're going to have to recover it. You're going to, you can't just release it to the atmosphere. There's going to be things down the road. I don't know how long that's going to be, but if we start working at it now, trying to, as much as possible, keep that refrigerant in the system, that's the best way to do it instead of just blowing it off. Oh, it's okay.
Of course. No, yeah, this is the case that we don't want to happen, but in case if it happens, probably less harm to environment compared to other synthetic refrigerants. Yeah, in order to just slowly going towards CO2 and using that, I just found that quite interesting to show that the CO2 proposed to be the kind of a first refrigerants back in 1850 with, I guess, water, ammonia, sulfide dioxide, and probably
That was a tough refrigerant. I've talked to some people working on that, and it's stuff
yeah.
that
So those are the first refrigerant back in 1850, and then it's completely displaced by CFCs in 1960. So they stopped using CO2 anymore from 1960 to 1991, and then from 1991 there has been a renewed interest in using CO2 for the system, and now everybody is talking about using CO2 for different applications.
it's going to continue to grow. Like I know it was Gustav Lawrence, and I think in 1987 or 89 he really started a thing, and I see you have it on 91 there. And now we're 30 some years. In the next 20 years, we're going to see a lot of CO2 and natural refrigerants out there. So
Of course, yeah. It's just a question of finding the best application and how to use the system and how to design it properly so that you get the best out of this refrigerant. But absolutely, in my opinion, also the natural refrigerants in future.
yeah, and I keep talking to people about it. We just the whole thing is to prepare yourself. Like I get emails all the time. People just why are you talking about this stuff? This is not going anywhere. It's dangerous, and people are going to get hurt. You can get hurt with any refrigerant. You need to be safe. We are in a skilled trade. We're refrigeration technicians, engineers, and we need to learn and teach ourselves and develop our skills to work with these refrigerants. Like CO2, 1850, they were working on it. Ammonia, they started in 1850, and they still using ammonia. So you have to be safe. It's all about being safe, but you need to learn and develop your skills so you can be safe.
Yeah, exactly. I guess we have a question, Trevor. Do you want to answer them now or?
Sure. So, what piping, a pipe material in the borehole for our 744? So, what are they, you guys, that was actually being put in the boreholes?
Yeah, the conventional system, if you run it for only heating application, of course, copper can do the job. But normally in our system recently, we used like the recent boreholes that we drilled, we used stainless steel piping. But this is what I'm gonna talk about in the end of the presentation, that even plastic can be used for CO2. That's the interesting part of that, the presentation that I'm gonna talk about. Yeah, how much CO2 is needed for a house which need 9 kilowatt heat? I need to come back to this later.
2.5 ton, 3 ton.
Yeah, for that, 3 ton, probably we might need. It really depends the pipe sizes and number of boreholes, but I can tell how many boreholes probably we need for that. Like if we drill, for example, 100 meter, which is not recommended for direct expansion, but again, for CO2 is a possibility. Because when it comes to that, that's a good question, because I forgot to mention about the depth of the borehole in direct expansion compared to secondary loop. Secondary loop, they drill even like up to 200 something, as long as you size the pump correctly so that you overcome the pressure drop. There is no problem for circulation. But direct expansion, because of the oil issue and other problems, they tend to size it not as deep as like 30 meters, like 100 feet, not more than that. In most projects, this is what they do. But again, for CO2 is not going to be an issue. So we even did that for 100 meters, and there is no problem to have longer boreholes for direct expansion using CO2. But for 9 kilowatt, probably we might need two of those 100, because the heat extraction could be quite efficient. For direct expansion, probably we need two of those 100-meter boreholes, but it really depends how much CO2. It really depends on the pipe sizes.
Yeah, we can figure that out later. But this is something that you need to know. And that's interesting to me because with synthetic refrigerants now, with direct expansion, you're only going to go 30 meters, 100 feet. Now with CO2, since there's so much velocity, so much, you can move more, you can do a deeper one. So that could be an advantage as well, I would say.
Yeah, definitely. This is gonna be a great advantage, because when it comes to direct expansion using different refrigerant like synthetic refrigerant, you need to increase the number of boreholes, because you cannot drill deeper than 30 meters, for example. But for CO2, you can have your boreholes 3 times deeper than the normal system. So imagine, instead of drilling 3 boreholes, you're gonna drill 1 borehole, but deeper, of course. If the land and also the distribution is an issue, because when you have many number of boreholes, especially for direct expansion, also the other problem is how to distribute the refrigerant into all those evenly, so that you don't get any problem or any efficiency problem for some of those boreholes.
So you're saying if I do say 6 boreholes, there could be a difference in each borehole with the temperature and the ground potentially, where you need to make sure that it's even distribution of heat.
The thing is, no, there is, in terms of ground temperature, probably they get all the same condition. However, when you distribute, you have to, in terms of pipe sizes, everything, and also the pipe that you run from the system to each borehole, you have to make sure when you distribute, you send equal amount of refrigerant to each one of them. Because if you have different refrigerant flow in different boreholes, then you get different performance.
Okay.
So when you have different performance, it means that you extract less from one borehole compared to another one. And always one in the vicinity of one borehole is colder than in the vicinity of another one because you extracted more energy from one compared to another one. So it's always one is going to perform less than the other one. Over time is going to get even worse because you extract more energy from that one and the temperature decreases. So it's very important that we distribute refrigerant evenly for the boreholes that we have. And this is also another thing that probably CO2 could be an advantage for CO2 because distribution of liquid CO2, for example, to different boreholes could be less challenging compared to another refrigerants. So these are all benefits or advantages of using CO2 for direct expansion system. But honestly, the last 10 years I'm doing research, still I believe direct expansion system is very good system for residential application, not for big system or light commercial application, not very big projects like you need 200 boreholes or 300 boreholes. When it comes to, let's say, 5 boreholes or less than that, probably this direct expansion is going to be the best system. But this is my opinion on on that.
Well, yeah, no, I work with some contractors that I don't think they're with CO2 yet, but they install a ton geothermal or ground source heat pump, sorry, and they continue, it continues to grow. I'd love to hear their comments too. I'm going to reach out to them, see if have they ever done any with CO2 yet.
Yeah, I guess all the your audience and Trevor know about those benefits of CO2, so I'm gonna, but it's always good to go through them rapidly to just to make sure that we all be aware of those advantages, or either environmentally or operational or like cost wise. There are some benefits for CO2: non-toxic, non-flammable, non-corrosive. The ozone depleting potential is 0, global warming potential 1, large carbon footprint reduction because of the refrigerant,
Yep.
low critical temperature, good heat transfer characteristics, is always 4 times better than the heat transfer coefficient, is better than other refrigerants that has been used for heating and
So
cooling
which one is
applications.
I asked this question to lots of people. Which one is the best heat transfer refrigerant? Is it going to be a natural refrigerant over a synthetic? Ammonia is really good. I know I was always told ammonia is one of the best heat transfer one. To you, which one has the best?
In terms of, I never used the ammonia in my the direct expansion calculation or modeling system, but using other refrigerant, always in terms of heat transfer coefficients, CO2 is the best. Like in terms of, I never compared that with ammonia, but with other refrigerant that is used for heat pump application, always CO2 is giving the highest heat transfer coefficient.
And this is where you can have smaller stuff like smaller pipes, smaller. Is that
Yeah, surface area, smaller pipe, surface area, basically for heat transfer.
so? That means smaller equipment as well. Like I was at a site where they're using 1234 ZE, I think, and they said if they use propane, the system would be half the size. Well, maybe not half the size, but it'd be way smaller than using that refrigerant just because of the coefficient.
Of course, that's what I saw. I guess among the refrigerants that I used to for the comparison, the R1234YF was probably, we need the biggest pipe among those refrigerants that I use for simulation. I'm gonna show you the result later, but this is what I also found, that it's not as close to CO2, for example. And in terms of cost, also less expensive. And there is, like, it's a future-proof refrigerant. There is no way that we say, okay, let's stop using CO2 and compared to other existing refrigerant, and smaller heat pump components, as we always mention, because of high pressure and other better or superior thermophysical property of CO2.
There's two on there: higher cooling capacity and higher energy density. Can you explain those two there?
Yeah,
So
it's mostly when we say that we can transfer, like with the specific mass flow rate of CO2, we can transfer more energy compared to other refrigerant. So this comes to higher energy density. And also when we talk about, when we go all the way from saturated liquid to saturated vapor, that the phase change and the latent heat of evaporation or condensation compared to other refrigerant is, some other refrigerant is bigger. So That's why we
Okay.
can get higher cooling capacity. And especially for low temperature application, this is pretty good compared to other refrigerants. When we started doing research on ground source heat pump, especially direct expansion system, we performed some life cycle cost analysis to see when we say that ground source heat pump systems are not, in terms of payback period, you get a pretty long payback period, how we can reduce that, and at what point we say, okay, this is going to be good in terms of cost for the system for a small residential unit. When I say small residential, I'm talking about a single family house in Canada, for example, in cold, like in Montreal, for example, small family, single family house. So we perform, you see on the left, bunch of curves that I'm not going to explain all of them. I just trying to say that these curves, as you can see in the arrow, this is from properly sized boreholes to undersized or oversized systems. So when you go from here to there, the curves that you see over there, so this one is the properly sized curve, and when you go up, those are either undersized or oversized. This axis is showing the relative payback period of ground source heat pump compared to air source heat pump. So we have two very efficient options that we can install for our house. One is air source and one is ground source. So we want to see the difference in terms of payback period between these two. And at that time that we started the research, it was it was 2015 maybe, or 14. That's why the price to install for the borehole cost per meter of a borehole was almost $60. I know that nowadays is more expensive, probably $100 or 120, but at that time it was $60 per meter. So we were kind of here. Compare like the ground source heat pump compared to air source in terms of payback period, we always have to wait 18 more years to get the investment, the difference between the investment in ground source or air source and air source heat pump. So 18 more years we have to wait until we get the money back from the air source investment. We have to wait another 18 years to get the investment in terms of investment in the ground source heat pump by reducing the cost of operating the system, basically energy saving that we
Okay.
get.
Okay. So right now there's air source heat pumps going in everywhere across Canada. Like there's governments giving tons of incentives and stuff like that. So this here is where you just got your evaporator condenser outside, your large outside the side of your house, and then inside is your evaporator and condenser, and they switch back and forth if you're doing heating or cooling. So you're saying your payback on an air source heat pump is 18 years back when you guys did this? That was
No, the 18 years is the difference between the payback between a ground source heat pump and air source heat pump. Imagine air source heat pump is, I don't know, 3-4 years of payback period you
yeah.
get, but ground source heat pump is 18 years on top of that.
Wow, that no wonder they weren't selling
Yeah, but
then.
for a residential application, I have to say, but for definitely for commercial application is always an option. Like among the options you have for the project, it's always ground source heat pump could be one of the best. But for residential application, this is not, in terms of payback period, is pretty long. But then we wanted to understand how much if we reduce the ground, because the major cost of the project is the ground heat exchanger installation. So over 50% of the cost is associated with the ground heat exchanger installation. So if we want to do something, because the heat pump is fixed, so we cannot much reduce that much, like the cost of the heat pump.
Yeah, it's gonna be
So
similar to what the air source heat pump is. Like it's similar components, similar size, but it's getting that equipment behind somebody's house and putting this big machinery and drilling holes into the ground. That's the cost.
that's expensive part, and it's over 50-60% sometimes. So we understood that if we reduce the installation cost from 60 to $30 per meter, then we get to the point that only we need couple of more years to get the extra investment on ground source heat pump compared to air source heat pump. That's a major barrier, the installation cost of ground source heat pump for market adoption of the technology. So basically, if we can reduce that twice, like make it half of the installation cost of a ground heat exchanger, then we can get a pretty good payback period Imagine only 3 years waiting more to get the money, the extra investment on ground source heat pump compared to the air source. So it makes it pretty good option to be considered always if we can reduce by half the installation cost. That's why we wanted to see how we can achieve that by using CO2, of course. So here, that's why we started to compare different refrigerants to see which one is probably the best for direct expansion system. What you see here, the circles, is the top view of the ground heat exchanger. So what you see from top is the hole, the bar hole, and you see the pipe, the U pipe, the cross section of the U pipe. So, and the rest, the area is filled with grout, which is try to maintain the thermal contact between the pipe and the ground. When you drill a hole, you put the U pipe and then you put cement or grout inside to make the thermal contact. These figures are for different refrigerants. For example, this one is a conventional secondary loop system. This is all in scale. So what you can see, you can compare visually how bigger the pipe is for different refrigerant, and also compared to secondary loop system when you have water antifreeze. So basically the first one over here is showing the dimensions for water when you have secondary loop system. But when it comes to direct expansion system, for example, this one is CO2, the pipes as you see. And then this one is R410A. This one is R22. Of course, we're not using R22 anymore, but this is just for the reference case. Just we do the comparison based on that just to show how different it is from R22 for the other refrigerant. This is R407C, which is the zeotropic refrigerant that we have glide in the evaporation and condensation. And this is for both R134A and also for R123YF is the same dimensions. So these two are pretty close to each other, these two refrigerants. And
so they continue to get bigger. So CO2, you have 11 millimeters there, so less than an inch, all the way up to over an inch or 14.2 mils. So it gets it. So that costs more money when you get bigger pipe, bigger diameters.
Of course, get more money, and also imagine if we can make if we want to make heat exchanger more compact than what you see here, then the one with smaller pipes, it's a better opportunity for having a compact system because you can put pipes closer to each other. However, for big pipes, because of the U bend at the end, you won't be able to make it closer than what you see, for example, in this case. But I have to mention that this is to extract the same amount of energy from the ground for all the cases you see here. So all the bar holes are extracting the same amount of energy from the ground. So then we need the different pipe sizes. And for all the cases, the pressure drop is almost negligible. So there is we size the pipe so that we don't get a big pressure drop. And all of them almost at zero pressure drop. It means that from inlet to the outlet, the pressure drop is not significant. So pretty close to zero for all of them. That's why you see different pipe sizes. If we want to compare, so if we want to focus on the left figure, as you can see, in order to extract the same amount of heat from the ground and at the specific borehole wall temperature, then if you see, for example, CO2, the first one over here, requires 20% less refrigerant flowing inside the borehole compared to R22. And this means it's 20% less refrigerant flowing inside. The pressure drop is a bit higher than R22, but the pumping power or the power required to compensate the pressure drop that you get is almost 80% less than R22 for CO2. For R410A, for example, these are the numbers. So again, you need less refrigerant to flow inside, to circulate inside the ground heat exchanger, but it's not as, like it's almost less than 10% less than R22. However, for CO2 is 20% less. And you can see, for example, for R123YF, you need over 20% more refrigerant flowing inside in order to get the same amount of heat out of the ground. So this is compared to R22 again. So comparing R1 to 3YF to CO2, you see this is 20% less than R22. This is over 20% more than. So that's a big difference. And also the pumping power or the power required to compensate pressure drop for this refrigerant is even more than R22. However, for CO2 is 80% less.
And just for the pumping power, that means more compressor. Is that what you mean?
Exactly. I mentioned this pumping power, but it means in direct expansion is going to be the compressor that requires like more energy to be able to compensate that the pressure drop between inlet and outlet of the ground heat exchanger.
And that's huge because if it's 80% less compressor you need, you can use a smaller compressor to get the same amount of.
When I say 80% is I'm referring to only the portion that we use for compensating the pressure drop inside the ground heat exchanger, because the most part of that power is required to lift from evaporation to condensation. I'm not talking about that portion, the small portion that takes care of the pressure difference between inlet and outlet of the evaporator. This is what I'm talking about. That portion for CO2 is 80% less compared to R22, for example.
And that's one big thing because pressure drop is not as a big of a deal with CO2 than a lot of other refrigerants because the pressures are so high.
Exactly, and also because of the superior thermophysical property of CO2. This is what I say is that we have pressure drop in CO2, and it could be even more significant than other refrigerant. But the power that you need to spend to compensate that pressure drop is way less than other refrigerants. And this is important. And the other thing is important also, when you get pressure drop in some other refrigerant, this translates into significant temperature drop in your system. For example, 100 kilopascal of pressure drop between inlet and outlet of the evaporator translates to almost 9-degree temperature difference in some other refrigerants. However, for CO2 is only less than 1 degree.
Wow. What is that in PSI pressure drop? 100 kilopascal.
100 kilopascal.
I'll look it up right now.
Yeah. On the right, however, if you remember the cross section of the borehole for CO2 compared to other, we used pretty small pipes. And this is not always a good thing to use the small pipes because you get less heat transfer area to exchange with the ground. So that's why in order to extract the same amount of energy from the ground, you need to run your ground heat exchanger 3 degrees lower than than R22, for example. So it means that imagine for R22, the evaporation temperature is 0 degrees C. In order to extract the same amount of energy as R22 with the small pipes that I showed you in the previous slide, you need to run your evaporator at -3 instead of 0. This is for a specific condition that I use for this calculation, which is kind of almost 100 watt of extraction from each meter of the borehole, which is kind of relatively big for ground heat exchanger. But using small pipes, it's not good because we don't get enough surface area, and then we need to run the evaporating temperature is going to be lower. This has a direct impact on the performance of the system, because imagine one system works at 0 evaporation and another system works at -3 evaporation up to the point that we need, for example, I don't know, 40 degree or 50 degrees C. That directly translates to performance or COP of the system. So we need to avoid that somehow. And we wanted to find a way to overcome that problem and just make that even more efficient than other refrigerants.
Having to run that at a lower temperature with CO2, that's an issue because that means a higher compression ratio. Is that right? Because that's a -3. So we got a higher compression rate, more work on the compressors, using more energy to get the same results. And that, just to be clear, that's because it's smaller tube, less surface area to take in, right?
Exactly. The pipe, if you remember, in order to size the pipe, we consider that the pressure drop for all refrigerants are the same, and then we size the pipe. But this pipe, smaller pipe for CO2, that does not have like as much surface area as other refrigerant. That's why you need to run your evaporation at lower temperature to extract the same amount of energy, and that directly impact your COP. And also, as you said, as you mentioned, like the compressor has to work harder, and the consumption, power consumption or electricity consumption is going to be more.
Yeah. I looked up that number as well. So 100 kilopascals equals 1 bar. I should have known this right off the top of my head, which is 14.5 psi.
Exactly.
That's a big difference in a standard refrigerant if you got a 14.5 psi pressure drop than CO2. Like, that's huge.
That's huge. Yeah, that's for some refrigerant. It's not acceptable. You cannot do that. Like, but for CO2, it's just only the temperature, the power consumption to compensate that is pretty insignificant, and also the temperature change is less than a degree. That's a good thing about CO2. And then, in order to summarize everything into one graph on the left, in order to summarize everything into one, we define something called potential improvement factor for CO2. Basically, it's this factor infers that the vertical single pipe borehole with CO2 can be more efficient, up to 79% compared to borehole with R22 at identical pipe surface area and fluid mass flow rate. If this is respected, like same mass flow rate, same surface area, then CO2 can be up to 80% more efficient than R22. And as you can see, the R123YF is less efficient than R22, like more than 20%, sorry. And the closest refrigerant to CO2 is going to be R410A, which is kind of good refrigerant, but the GWP is high. So it's 20% better than R22, R410A. This is what we mentioned about pressure drop and the impact on the temperature change. I'm trying to show you here on the right, the curves that you see. Each color is for one refrigerant. But you see, even if in direct expansion system, that's why it's pretty complex to simulate that, because even if you don't have pressure drop between inlet and outlet, still the pressure changes inside the borehole because of different components of pressure drop. You have friction pressure for friction, you have for acceleration, and you have for gravity. So those effects create pressure changes inside your borehole. And it doesn't matter if you inlet and outlet pressure is the same, still you experience different pressure along the pipe inside the ground. So that's why you see different profiles of temperature for different refrigerant. And as you can see, under same pressure drop in between inlet and outlet, for all those refrigerant, CO2 show you the most uniform temperature difference along the borehole depth. This axis is showing the depth of the borehole, and this is showing the fluid temperature change. So CO2, that's why CO2 can extract uniformly from the ground compared to any other refrigerant. Because the other refrigerant, the temperature changes significantly. And that's why, for example, if we focus on, for example, this R407C, the green dash line, this has a glide. So you see, the temperature increases significantly up to at the end of the borehole. This is coming down the fluid and then coming up, almost six degree difference between inlet and outlet. And imagine the second pipe can extract way less than the first pipe because of the temperature difference between the ground and the fluid. So that's why we say that CO2 is pretty good for direct expansion system, because we experience pretty uniform temperature from the inlet to the outlet. So the heat extraction is the same. It remains the same, and we don't change the performance along the borehole depth.
Can you talk about the three things you said for pressure loss, not pressure loss or temperature change? So I know one was friction.
Yeah, the friction, acceleration, and gravity there are three terms that we use to calculate the total pressure drop. So basically, the total pressure drop is created based with those three terms: acceleration, friction. It's not only friction. For most of cases, like when it comes to two-phase flow, of course, single-phase flow is only friction because the other terms are negligible. When we say that, for example, for single phase, when we have water circulation in the vertical pipe, for example, a U pipe, so the gravity, of course, we always have gravity, but the thing is that because the density remains the same from the beginning to the end, so the gravity effect for pressure drop is negligible. So you don't count for gravity, and also acceleration, because again, the density doesn't change significantly. You always don't consider the acceleration term for your pressure drop calculation. It's only friction.
Oh, yeah, that's so that's new to me. That's so
Yeah,
awesome.
but
Thank you.
for two-phase flow, because we start from liquid, we go all the way to vapor, then the density changes a lot. So then we need to, those terms also becomes important, gravity and also acceleration. We mentioned that the problem of CO2 is using small pipes. So how we can overcome that and how we can design a very efficient ground heat exchanger for CO2. So we came up with the idea of multi-pipe system. Imagine for R123YF, that had the biggest pipe dimensions. So imagine the total surface area that we have for that borehole. We get that number and we try to use the same surface area for CO2. But instead of having single pipe, we use multiple U pipes so that we get the same surface area as the R123YF or R134A refrigerant. So the same surface area as those, but with using multi-U, because if we use one single U, the pipes are very big for CO2 and we get oil return issues and other problems that we want to avoid. So we need to use small pipes, but how we can solve the problem of surface area, we can use multi-U pipes.
And so that would be now we talked about earlier, you got one borehole and you just put two pipes down. Now it's putting two or three U pipes in that same hole or four in that same hole. Instead of having to do four holes, boreholes, you just do one and you put four U pipes.
For U pipes, but I'm gonna tell you where we're gonna go at the end, because this is not to many people, and even to me, this is not in terms of installation cost, is gonna be even more costly, installing that four pipes in one borehole, because people are not used to people who install those systems are not used to do that, and that is still we're not solving the cost issue by proposing that. But just at the moment, what I'm trying to say that in order to address the heat transfer issue, we can come up with this, increasing the surface area by using multi-U pipe. So again, the same numbers that I want to show you. On top right, you see, of course, we increase the pressure drop significantly for CO2 with 4U pipe. Imagine, the pipes are pretty tiny, like very small pipes, you see. And 400, it means 4 times more pressure drop than R22. But you see, still the power we consume to compensate that is less than R22, still single pipe. Single U pipe, R22 we have to consume more energy to compensate the pressure drop of that compared to 4U pipe, even if we have 4 times pressure drop. And R410A with 2U, the closest refrigerant to CO2 is, as I mentioned, R410A. And for that, we cannot go further than 3U. You cannot install 4U and you keep the same mass flow. The pressure drop is going to be significant, huge, as you see, 8 times more than R22 single U pipe. And the power consumption to compensate that is over 6 times, almost 6 times, a bit less than 6 times of what we consume for R22. So what we can do, the most number of pipes for R410A probably is 2U. And I have to mention that for any other refrigerants that you saw in this study, we couldn't install even 2U pipe if we keep the same mass flow and we keep the same surface area. So the pressure drop is going to be significant and we are not able to do that. The only refrigerant that we can try 4U pipe or 3U pipe is CO2. And you see that compared to, this is the mass flow rate required for the 4U, for example, CO2 still over like almost 12, 13% is still less mass flow required for CO2 in this case, even compared to R22. And this on the left is showing that we solve the problem of evaporation temperature. For this specific case that we have relatively high extraction from the ground, we can run the evaporator 8 degrees warmer than R22.
That's huge. That's huge. But we're talking about theoretical, and 4 pipes in the ground is way more costly too, right? So, so
Yeah, still we're not solving the cost, because this is the main issue, was the main barrier is the cost. I agree that still running 4 pipes is not easy, and nobody likes doing that.
but you run at 8 degrees warmer, like that's huge because you got a smaller compression ratio. You're using less power to cool or heat in that space.
Exactly. But what we can do with this, imagine having those 8 pipes, like 4U pipes that we have, you can make it pretty compact, like closer to each other, because you're using tiny pipes. And instead of having pipes, you can create a block with plastic that has channels inside. And it's going to be one assembly. Like you have a 2-inch pipe, basically, with all those channels inside. And it's from plastic. And what you're going to do, you drill 2-inch and you put that plastic inside, and there is no need for further installation. So like installing each single U separately, because you would use pretty small channels or small pipe, there is a possibility to make them pretty close to each other and make it a 2-inch assembly, instead of like it's called prefabricated ground heat exchanger, instead of putting each pipe separately in the ground.
Okay, so this here, what we're looking at for anyone who's listening, so you get like a little 2-inch disc. There's 8 holes in it and one in the middle, and you're saying you use this plastic pipe that will go down into the ground, and you'd loop it up, and I guess you would have multiple ones of those going down on it just to keep it separated properly.
No, the thing is, that the whole assembly you can see over here, forget about the middle one. This is just to reduce the material. We're not going to do anything with that middle part. So these are the all 8 pipes or channels that you saw in the previous slide, but we try to make everything in one assembly, like having a block of a polymer or plastic that has those channels inside, and at the end they are all connected.
Okay, because CO2, we're working at a higher pressure. So what would the pressure be running through these pipes right now?
Those, even with 100 bar of pressure, because you're using a tiny channels, the channels inside those, they can resist high pressure with pretty small pipes. When, of course, you need a big pipe and high pressure, this is going to be problematic. You're not able to use plastic. But when you're talking about like a small, very tiny dimensions and diameter, and high pressure, still plastic. We have plastics that it can, like pretty small pipes that can go up to 100 bar pressure.
Yeah, I've seen some too at some shows where they're showing actually piping that you can pull and stretch that could potentially be refrigeration piping. The only thing is that oil. You got to make sure it's slow properly and put. So how would, if you use it this way? Because this is cool. So it's only 2 inches. You can smaller boreholes, and you drop this in. So you drop this into the ground, and you'd connect them all together. The normal ones would be straight. So you're dropping it in as a big U bend and as a big long straight for 30 meters or whatever. And you drew. How would this work going in the ground? Because I'm curious.
Yeah, the thing is, after drilling the hole, this still you need, like you drill a bit bigger than the 2-inch, so that you can insert that, and eventually you need, probably from the middle part you see here, you can inject some grout inside to get the perfect thermal contact. But imagine when you drill, you just insert, like you have the hole, like you unroll, for example, you have it. This is all, we haven't fabricated that yet, but this is the patented technology of NRCan, Natural
Okay.
Resources Canada. So it's already patented. So eventually, what is gonna be like the whole assembly in one. You can roll it like on this system over here, and then when we have the hole inside, then we unroll it and we insert it inside. Like when we put plastic for a secondary loop system, we unroll and we put the plastic pipe, even plastic U pipe, let's say, the high density polyethylene pipe inside the hole. So imagine we unroll this and put this inside the hole, and then we put grouts just to get the proper thermal contact. But what I'm trying to say is that there is no need anymore for having installed those separate U pipes inside the borehole, and then have all those connections and then grout, because this is the most expensive part. Like drilling, of course, is one, and also the material you use for those stainless steel piping. Imagine you have four U pipes from stainless steel, and you need to insert them all inside the hole, and then you grout it, and then do the connections of all those to your system. So it's going to be kind of one assembly, can be called prefabricated ground.
So this will reduce the cost because now you're not paying for stainless steel or copper going into the ground.
And also the installation cost in terms of the energy you consume to drill, because one part of the drilling process is the energy you put to drill the big holes. Like if you have 6-inch or 10-inch hole, it's way different, like the energy you consume, than smaller pipes, the smaller holes, like 2 inches. So also the kind of machine you're gonna use to drill that is gonna be probably much smaller and less costly in terms of the equipment you need to drill that. And as I mentioned, this is the technology of NRCan. And if anybody is interested, like to know more about this, probably the best thing is going to be contacting NRCan to get more information, or they can also email me. But yeah, that potentially could be one solution to residential ground source heat pump application, and we can significantly reduce the cost, even by what we mentioned at the beginning, by reducing the cost by half, to make it, in terms of payback period, close to air source heat pump at least. This is going to be one way to do the project this way, so that we can save it.
Yeah, that makes a lot of sense. So if you can reduce that cost, that's the big thing. But at the end of it, we need to reduce the power that it uses, and this CO2, as you showed me, is a potential of, it's going to use less power to heat or cool your home using this refrigerant.
Yeah, the other thing I have to mention about CO2 probably is the fact that when we talk about CO2, many people might say this is not, in terms of efficiency, is not good compared to other refrigerants. But if we find the right application, or if we design our system, because there are many possibilities in one project, there are many possibilities to optimize the system that we wanted to install. And I have to say, for ground source application, heat pump application, probably CO2 could be one of the best, because we always, especially for deep vertical ground source heat pump, because the one side is always a temperature of the ground, which is, imagine in Canada, around 10, from 9 to 12, probably different locations, different. But that side, which, imagine for heating application, that side is quite fixed, like at 10. And the other side is space heating. If we have a efficient space heating and we don't need high temp, we're talking about like 35 degree. Even we can heat the residential very efficient heating system. We can do that, 35, 40 max. So
Celsius, right? You're
yeah,
talking about?
Celsius, yeah.
Yeah.
So then ground source heat pump with CO2 could be a very good application, and especially for cooling, ground is going to be at, imagine again, 10, and it's going to be pretty low lift, and you get amazing COP for cooling of your house, if you would like to use it for cooling either.
That's very interesting. All these different technologies out there. I've learned a lot today. I still have a lot of questions. Just curious on, has any of these been installed? Like, is there many applications out there with CO2 and a ground source heat pump in a residential or like commercial application?
When we started doing research on CO2 for direct expansion, there were, I guess, quite a few systems installed in US. And then after we finished some research and finding that this system could be efficient for heating application and also cooling, we installed one at Natural Resources Canada, CanMet Energy. So in order to cool and heat the specific part of the building. So this project is going to be finished, I believe, this year, and it's going to be operational next year, or even at the end of this winter, hopefully. And then probably people, if they want know more about the performance and how the system works over different conditions, CanMet Energy can provide more information on.
Yeah, because that's what everyone's going to want. So there are a few installations out there, but you here in Canada is going to be that's going to be one of the first ones. And CanMet Energy is
CanMet Energy. I'm just trying to think if there is other installation CO2 direct expansion in Canada, but I believe I don't remember any. But
that's okay. I'll find out. I'll reach out to a bunch of different people from different countries and ask them, see where they're at with that, because it's good, because people are going to want to know and understand, like, what is the energy consumption, how is it working, what issues have you ran in, what are the positive, what is the cons of this application. Because it's like anything, I believe, is that you need to select the right equipment for the right application designed properly, because if not, especially installation, commissioning, startup, all has to go together properly, or you're not going to get the results you're looking for on any equipment. It doesn't really matter what it is.
exactly, yeah, that's the most important thing, especially for ground source heat pump. The right sizing is going to be a very important point, like to size it properly so that you get the best out of the system. But definitely there are some systems with CO2 in US, but in Canada, I don't remember.
Okay.
Yeah.
So any final thoughts you want to leave with the audience, Parham?
No, as I mentioned, I think CO2, like if residential application, if we think that ground source heat pump can solve the energy consumption or energy saving or any other environmental impact of either refrigerants or the existing system like gas boilers, probably one option could be CO2 direct expansion units for residential application. And still, I believe, my opinion, direct expansion system ground source heat pump probably is not going to be a solution for big commercial buildings or big projects, mostly for a small residential or probably light commercial buildings. CO2 ground source heat pump direct expansion could be a excellent solution, because in terms of performance is the best.
Yeah, it looks like it from the numbers that I've seen here. Awesome, Parham. How can people get a hold of you if they want to learn more about these solutions? I know you said you're going to send me some links. I'll put it in the show notes.
I can definitely do that, sending some more details about the calculations and the study that we have done before. And also I can, of course, through LinkedIn always, this is one way we can connect, and I'll be happy to answer any questions.
Fantastic. I want to thank you so much, Parham, for taking the time to chat with me, share some knowledge on ground source heat pump. I learned quite a few things. And as always, like, share this information with others. There's a lot of people out there who want to learn more about CO2, want to learn more about ground source heat pumps. Really appreciate you taking the time to do this. And I'll see you at the next CO2 Monday. Thank you, everyone.
Yeah, thank you so much.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.